Record to the cloud. Okay. All right. Well, let's get started. So we're just going to go through a forced heat equation problem. And this can kind of help just sort of revisit ideas from unforced problems too. So let's just jump right into it. So let's say that we have a bar that's being forced on its interior by this time decaying function that's also spatially varying. So you're heating this bar from the interior, but that amount that you're heating it, right, is decaying by some amount. This is for t greater than 0, and then I think our domain is 0 to pi. And we'll just impose Dirichlet boundary conditions. But one of them will be 1, okay? So I have an inhomogeneous boundary condition. So we get to talk a bit about how that's going to work. And then I'll just say the bar starts out with a constant initial condition. So immediately you might say, yeah, well, there's a discontinuity, right, between the initial condition and the boundary condition. So the initial and boundary data don't agree well, but on the interior, because of the smoothing properties of our heat kernel, we know that immediately we'll have a C infinity function once we move away from the boundaries, right? So this whole issue here, right, with this corner having a discontinuity, okay? That means we have, you know, an L2 defined data. We don't have, like, you know, C2 initial and boundary data, okay? But separation of variables can handle that, and we'll basically L2 converge to a solution. Okay, so let's do the first part of the problem. Let's just find a solution to the stationary problem. Okay, so we're going to actually build up to the time varying solution. What's the stationary problem? Well, remember, as we well, maybe you haven't watched this lecture yet, but in the stationary problem of the heat equation actually is it's like a Poisson equation because you drop out the time derivative. Okay, so why do this? Well, this sort of tells you maybe something that you can subtract off from the solution to see how everything else is evolving and collapsing to the stationary solution over time. So if you had an undergrad PDE course, maybe you did this before, okay? So the solution, right, is going to be what? Well, in the limit, as t goes to infinity, e to the minus sine 3x, that's just going to be 0, right? So the PDE, okay, becomes what? Well, remember that a stationary solution, right, should have no time derivative, okay, but it will have a space derivative, right? So this is going to be minus u bar prime prime of x equals 0. So we just have an ODE, okay? U bar, then the general solution to this, what's that going to be? Ignoring the boundary conditions for now. What's a function where if I differentiate it twice, I get 0?
Line.
Yep, ax plus b. Okay, what do I know about my boundary conditions now? So remember, in the long-term solution, the initial condition is no longer relevant, right? Because I'm out at infinity, right? But what is still relevant is the boundary conditions, okay? So in addition here, I'm going to take the boundary conditions, okay? And I know that, well, this is true for all t greater than 0, so u bar of 0 needs to equal 0, okay? So that is going to be equal to b, so that implies, of course, that b equals 0, okay? So b goes away. U bar of pi now equals 1. So that's equal to a pi. So that implies that a is equal to 1 over pi. So that implies that u bar is equal to x over pi. Okay, so that's our stationary solution. Good. Okay, so now the way I wrote this problem, actually I'm going to kind of guide us through solving the main problem. Okay, so the next step along the way is to subtract u bar from u. And you'll get the leftover part that kind of collapses to the stationary solution over time. Okay, so part B of this problem, and I'm just gonna, I'll send you this problem too, so you can see it. Subtract u bar from u, and now formulate, okay, an IBVP for v of xt is equal to u of xt minus u bar of x, okay? That's not hard. We can just use linearity, okay? So v sub t, in this case, is going to equal u sub t. That's it, right? Because that part goes away. V sub xx is going to equal u sub xx, right, minus u bar prime prime. But remember, u bar prime prime is 0, so that goes away. So we have that v sub t equals u sub t and v sub xx equals u sub x. So that just means that v sub t minus v sub xx is just equal to what u sub t minus u sub xx is equal to, which is just the original problem, e to the minus t sine of 3x, right? So you're like, well, are we just spinning our wheels here because it doesn't look like we've gotten anywhere, okay? Well, we know one thing now is that v of 0 t is going to equal u of 0 t minus u bar of 0, right? Which u of 0 t was 0. This is 0 too, so this is 0. But v of pi t is going to equal u of pi t minus u bar of pi t, right? And if I'll just briefly go back now, right? U of pi t is 1, and u bar of pi is going to be equal to 1. So this process has allowed us to at least homogenize our boundary conditions, which is going to make our eigenvalue problem easier when we set up separation of variables. Okay. The last thing is I now have v of x0 is equal to u of x0, which remember was 1 minus u bar of x. So this is going to be 1 minus x over pi. Okay. So that's my new IBVP, right? Right here that I can solve using separation of variables.